So till now we have seen parabolic reflectors where there was a feed given, and from the feed the rays will be onto the parabolic reflector and it will be converted into parabolic rays. So next one is lens antenna. From the name itself you can make out, in this it consists of a lens which will act as the antenna. So here also there will be a source, and the waves from the source in the spherical wavefront will be converted by the lens antenna. It can be either concave or convex. So this lens will collimate the electromagnetic rays. Collimate in the sense it will be from the focal point, whichever is diverging, it will be converted into parallel wavefront. That is known as collimating of the electromagnetic rays. So depending upon whether it is working as a receiving antenna or transmitting antenna, it will collimate the rays or it will diverge the rays, or it will convex the rays. So either it will be depending upon whether it is receiving or transmitting. Transmitting means it will be converted to parallel wavefront, and receiving means all the rays coming in parallel wavefront will be falling onto the focus. So this is how the antenna will be. In this, there are mainly two types of antennas. One is delay lens and the other one is fast lens. So first one is delay lens antenna. Delay lens antenna will consist of a concave lens. So in this case, what happens by the name delay lens is because in this case, the wave will get retarded. So this is the source. So from the source, this is the source. So from the source, the waves are radiated. So when it is falling onto the lens, the wave will get retarded. So there will be a delay in the waves traveling. So we can tell that in this case, electrical path length is increased. That is the path that it has to travel will be increased. So that means the wave will be retarded. So what do you mean by electrical path length? It is the path length which we are writing in terms of wavelength. So in this case, the electrical path length is increased by the lens media. So and the wave will be retarded. As the wave is retarded, we also call it as delay lens. Now next type is fast lens antenna. So in case of fast lens antenna, we use convex lens. So in this case, what happens is because of the material or the lens used, the wave will decrease. The electrical path length is decreased by the lens medium. So in this case, the electrical length is decreased. So we also call it as, so the wave will get accelerated. In this case, as it is transmitted through this convex lens, the wave will get accelerated. So the path length will decrease. And so this is known as fast lens antenna. So example for this one is E-plane metal lens antenna. So you have two types of delay lens antenna and fast lens antenna. Name itself you can make out. Delay lens antenna means the wave get retarded. And example for this is dielectric lenses. And in case of fast lens antenna, the wave get accelerated or the electrical length path length is decreased. The example for this is E-plane metal lens antenna, which will be discussed later. What is the basic principle of lens antenna? So when you are considering a lens antenna, suppose you consider this is the source. At this point, it is radiating waves. So from the source, when it is radiating, it will generate a spherical wavefront. And let us consider the distance from the source to the lens is the focal length. So these spherical waves that will be falling onto the lens. This is a concave lens. So it will be falling onto this lens. So what happens is it will get refracted. Refraction takes place and all these rays what is falling onto the concave lens will be becoming, it will be collimated to obtain a plane wavefront. So this is the basic principle. So what is happening is from the source whatever is generated all get converted to spherical wavefront and it is generating as plane wavefront. So depending upon whether it is actually transmitting antenna or the receiving antenna. So transmitting antenna means all will be parallel rays, but receiving antenna means these parallel rays will be falling onto the lens. It will be coming and it will be converging onto the source. So this is the basic principle of lens antenna. Now the feed systems of lens antenna. So as I've told you, in this case also, like parabolic reflector, you need a feed and then in front of that you are placing a lens antenna. So the feed usually used will be a horn antenna. A horn antenna is used to feed the lens antenna. So you have a means the aperture dimension of the horn is selected equal to the focal length of the lens antenna. So that is how we select it. Usually the feed used will be horn antenna. Horn antenna already have studied. This is how horn antenna looks like. So it will have a waveguide and which has been flared out. So this will be the flare angle and here you will be placing the lens antenna. Now this is a derivation, that is when you consider a non-metallic dielectric lens antenna, what will be the final equation for this? You have to find out. So now let us consider that this is a non-metallic dielectric lens antenna. So this is a lens antenna. So here you have the point source. So this point source will be generating different rays. So all these rays, either it can fall onto the lens antenna or if it is going beyond the limit, then like it's like an asymptote will be going like this. So now we have to derive the equation for this non-metallic dielectric lens antenna. So this is usually this analysis is done by using ray analysis method of geometrical optics. So let us consider an isotropic point source that is placed at the focal point, and this will act as a primary antenna that will produce a spherical wavefront, and that will be falling onto the lens antenna, which will be converted into parallel rays. So now here we have to consider Fermat's principle. That is, we have to consider the principle of Fermat's principle, that which states that this is also known as principle of equality of path length. Principle of equality of path length. That is, in order for the lens antenna to convert spherical wavefront to plane wavefront, all the path from the point source to lens must have same electrical length. That is, as we know that when the wave is traveling from here to the lens, all the waves that is being pointing on to this lens should be converted to plane wavefront. So how it can convert to plane wavefront? It can convert to plane wavefront only if the distance of all the rays are the same. That is Fermat's equality principle. So now here from this diagram, so all the path length should be electrical path length should be the same. So when you consider here, you can see here different paths are there. So we will consider two paths. So as per the principle, it should be the same. So here you can see that the distances 0 P1 should be equal to you're able to see, right?
Yes, ma'am.
Okay. So here the So as I've told you, the path length should be the same. So we can make out that from this, the path should be the same. So we can consider two paths. That is, one is 0 P1. So that should be equal to 0 Q1 Q2. So according to principle of Fermat's principle, in order to convert the spherical wavefront to plane wavefront, the electrical path length should be the same. So we can consider two paths, that is 0 P1 will be equal to 0 Q1 Q2. That is what we are doing here. So also we can make out that OP is equal to what? OP will be equal to OQ1. It will be equal to OQ1. So we have to find this distance. So if you consider here, OP is equal to R. It is equal to R. So, and also we are considering electrical path length. Electrical path length means whatever is the distance divided by lambda you have to consider. So, as it is outside the lens medium, this distance is R. So, R divided by lambda naught. So, that is OP. So, that will be equal to OQ Q1. OQ is equal to L. So that means we can write it as L divided by lambda naught. Now we have to find out this distance QQ1. So in order to find out QQ1, from this triangle you can make out, from OPQ1 you can make out OQ1 is equal to R sine theta. It is equal to R cos theta. It is adjacent, so it is equal to R cos theta. So this OQ1 total will be equal to R cos theta. But we want the distance QQ1. So QQ1 will be what? R cos theta minus L will give you QQ1. So also, and also here we are considering the wavelength is inside the lens medium. So we have to divide it by lambda d. So that will become r cos theta minus L divided by lambda d. So finally we can write this equation as r divided by lambda naught will be equal to, which is equal to OP. That will be equal to the path, that is equal to the path OQ1. OQ is equal to what? L divided by lambda naught. And what is QQ1? QQ1 is equal to R cos theta minus L divided by inside the medium. So it will be lambda D. So we can write this equation. That is R by lambda naught is equal to L by lambda naught plus R cos theta minus L divided by lambda D. So where lambda naught is equal to free space wavelength and lambda d is the wavelength inside the lens. Now multiply this equation 1 by lambda naught. If you are multiplying with 1 by lambda naught, so here it will get cancelled. This R is equal to L plus R cos theta minus L into, taking this lambda naught to this side, this becomes into lambda naught by lambda. So this will be the equation. Now next is, we can also write the refractive index of lens. Usually the refractive index is given by the formula velocity of free space divided by velocity in the lens. Here we are considering inside the lens. So velocity of free space divided by velocity in lens. So we can write this as velocity of free space is C divided by velocity in lens is Vd is equal to Vd. So we can write C is equal to, and also we know that C is equal to F into lambda. So C can be written as F into lambda naught and Vd can be written as F into lambda d. So F will get cancelled. So what is remaining will be lambda naught divided by lambda d. So now in the previous equation, that is equation 2, we have lambda naught divided by lambda d. So lambda naught divided by lambda d, we have obtained it as equal to n. We can write the equation as r is equal to L plus r cos theta minus L into n. We'll get it as into n. Now next is also we can write the refractive index can be expressed in terms of dielectric constant of medium. Already we know that refractive index n is equal to C by Vd, that is velocity in free space divided by velocity inside the lens. So C is given by the formula, usual formula 1 divided by root of mu naught epsilon naught, and the lens medium we can write it as 1 by root of mu epsilon. So here mu can be written as what? Mu naught mu r, and epsilon can be written epsilon naught epsilon r. So epsilon naught and epsilon r will get cancelled. So we can write this as equal to root of mu epsilon divided by, taking this to this side, we can write it as, we can write this as root of mu epsilon divided by root of mu naught epsilon naught. So if you substitute, this will get cancelled. What is mu naught will get cancelled if you substitute this. So what is remaining will be n is equal to root of mu r epsilon r. So this is the final formula. And if you are considering non-magnetic material, mu r will be equal to 1. So mu r equal to 1 means this will this will be can be removed. So directly we will get n is equal to root of epsilon r. So here usually the question asked is, according to the principle of equality of path length, prove that refractive index is equal to root of epsilon r. That is usually how it will be asked.